are various AC bridges. Some of the AC bridges are used to measure inductance. So, firstly, we will study measurement of inductance. By using many AC bridges, a bunch of AC bridges, we can measure inductance. The first and basic bridge which is used to measure inductance is Maxwell's inductance bridge, or Maxwell's bridge simply. Okay, Maxwell's inductance bridge. This is the basic bridge which we will prefer to measure the inductance. So here the bridge looks like this. So please don't confine to the convention which I am following, but understand the concept. You can use the unknown inductance anywhere, either in first term, second, or third, or fourth. But you need to obtain the balance condition, and you need to find, or you need to get the balance equations easily. Getting a faster convergence. Faster convergence means you need to obtain the balance of this bridge in a faster way, and the balance equations must be simple to understand, simple to analyze. This is the major goal in designing any type of AC bridge. Okay, so here, as I said earlier, I'm considering my test coil whose inductance is to be determined. Okay, R1 and L1, these are the unknown resistance and unknown inductance of the test coil. Test coil is, in the sense, the inductance of this coil which we are finding, and this is placed in the first arm, and in the second arm I am placing another resistance and inductance. So this inductance is having some internal resistance which I am considering. So I am considering this as L2, and the resistance of this inductance, because you will have some more internal resistance of the inductor. I am considering this as L2 R2, and this is R2. As these two are placed in second arm, I am giving the name 2, and as this is placed in the first arm, I am considering this as 1. In addition to that, you also have one more resistance I am assuming here, and this is one more resistance. As these are pure resistances, I am considering this as R3 and this as R4. Okay, so let me write like this. Here, what is R1, L1, all these things. Let me write here itself. R1 and L1, all this is a test coil, test unknown coil, because we need to find the resistance and inductance of this coil. As I want to measure the inductance of this coil, I am considering this coil as the test coil. Okay, so test unknown coil or unknown test coil, whatever it may be. Let me write it properly. Unknown test coil. Unknown test coil. We need to find this. And R2 is uh, R2 is the resistance in series with L2. Known, this is known resistance, known standard resistance. Okay, known standard resistance, and L2 is nothing but it is also a known value, known standard inductance, known standard inductance with the internal resistance, with the internal resistance R2, because practically any inductor has some internal resistance, right? So with the internal resistance R2. Now what about the remaining things? Remaining is R3 and R4, R3 and R4. These are also known because if one is unknown, the remaining three must be known in order to get the balance equation, or in order to um, uh, find the unknown elements like resistance and inductance. One arm elements must be known and the remaining three arm elements must be uh, sorry, one arm elements must be unknown and the remaining three arm elements must be known. Okay, so these are known resistances, known resistances, and they are of non-inductive nature. Known resistances of non-inductive nature, because there is no inductive nature present in the resistances with non-inductive nature. Okay, so this is about all the four arm elements, and here I can connect the detector. So here I can connect the detector, and across the remaining two opposite terminals I can connect the source. So every time I will not draw the source and detectors. You need to understand that, right? Now what about these voltages? What is this voltage? This voltage is E1, and I am assuming the voltage across the third arm as E3, and this voltage as E2, and this voltage as E4. Okay, so we all know that, and what is the source voltage? Source voltage is E, I am assuming. So from the KVL, the phasor summation of E1 and E3 gives us E, or the phasor summation of E2 and E4 gives us E. Okay, now E is nothing but E1 plus E3, or E can also be written as E2 plus E4. Why I am writing this, you can understand from the phasor diagram, the reason why I am writing these equations. Okay, while we are drawing the phasor diagram for this bridge, you can understand that fact. Now first find the bridge balance condition. Okay, so under balanced condition, under balanced condition, the current through the detector will be equal to 0. The current through the detector will be equal to 0. In that particular case, the product of the impedances of these two opposite arms 1 and 4 must be equal to the product of the impedances of these two opposite arms 2 and 3. Now let me write the balance condition. So Z1 into Z4 must be equal to Z2 into Z3. Now what is Z1? Z1 is the series combination of these two resistance and inductance. Okay, so I can write in place of Z1, which is R1 plus j omega L1 multiplied with, and Z4. What is Z4? R4, and it is equal to, what is Z2? S1. So here I can take the equivalent resistance for the entire element as R2 plus small r2. So I am considering this as R2 plus small r2 plus j omega L2 multiplied with R3, because Z3 is R3. Okay, now just simplify this, just expand this equation, these expressions in the LHS side and in RHS side. What you will get? R1 into R4 plus j omega L1 into R4, and it is equal to, and in addition to that you also have, okay, R1 into R4 plus j omega L1 into R4, and what is the next one? R2 plus small r2 multiplied with R3 plus j omega L2 into R3. Okay, so as this resistance is very much lesser than is capital R2, we will usually neglect this resistance. Okay, so now if you equate the real and imaginary terms, equate real and imaginary terms. If you equate the real and imaginary terms, if you equate the real and imaginary terms, what is the real term? Here in the LHS side, R1 into R4. What is the real term in the RHS side? It is and it is equal to R2 plus small r2 into R3. Now from this equation I can write R1, because what I need is actually the resistance of this unknown test coil. The resistance of the unknown test coil is to be determined. This is the purpose of connecting all these four arms like this. Now R1 is equal to R2 plus small r2 into R3 total divided with capital R4. So this is the equation which is useful to find the unknown resistance R1 in terms of the known resistances R2, R3 and R4. Okay, all these are the known resistances. Similarly, by equating the imaginary terms will get j omega L1 into R4 is equal to j omega L2 into R3. Now cancelling j omega and j omega, you will get L1 into R4 is equal to L2 into R3. From this equation I can write L1 as L2 into R3 divided by R4. Okay, I hope I have done it correctly. If there is any mistake in my calculation, please let me know immediately so that I can rectify. So this is L1, inductance L1, and this is the resistance R1 of the test coil. Okay, see here, if here what actually we will do is, here what are the common terms in both the equation. So consider this as the first equation and consider this as the second equation. In equations 1 and 2, what are the common terms? The common terms are R3 and R4 are common, common. Is it right or not? And what are the uncommon terms? Forget about this R2, it is a very lesser value, and we cannot change this. We can change only R2 and L2. So the uncommon terms are R2 and L2. These are uncommon terms. If you change the common terms, both will change. R1 and L1 will change. If both changes, it takes a long time to get the null condition. Okay, so you cannot get the balance condition easily. So changing the common terms will create a sliding balance. What is meant by sliding balance? The balance cannot be obtained easily. It will take a long period of time or more number of iterations, more number of variations in R3 and R4 we need to do in order to get the balance condition. So we call this way of obtaining the balance condition as sliding balance. Whereas when you change R2 and L2, then the R1 and L1 will change independently. Okay, so the change in R1 is independent of the change in L1, so that we'll get faster convergence. Okay, so this type of convergence we call this as faster convergence. Faster convergence is possible when we change the uncommon elements, not the common elements. Okay, so now let me write the equations again. R1 is equal to R2 plus R2 into R3 divided by R4, and L1 is equal to L2 into R3 divided by R4. Okay. Now what we will do? We will not change this, as these are elements, common elements. When we change this, it takes a longer period of time to get the sliding balance. Hence, we will fix these resistances. We'll keep this resistance as fixed, and we will make this resistance and inductance as variable. Why we are following this procedure? Because by changing R3 and R4, R1 and L1 will be dependent on each other, so that it takes a long time to get the balance condition. We call this type of balance as a sliding balance. Hence, we will fix these resistances. Okay, so these two are fixed now. R3 and R4 are fixed, whereas we'll change these two elements because these are uncommon elements which changes R1 and L1 independently. The change in R1 is independent of the change in R1 L1, so there is a chance to get the faster convergence. Hence we choose L2 and R2 as variable. L2 and R2 as variable terms, are variable elements. Okay, so this is about the balance condition or the balance equation in case of Maxwell inductance bridge, and it is a very basic bridge, and obtaining the balance equation is also a very simple process. But as there is no capacitance available in this bridge, we cannot easily evaluate the quality factor of this coil. Quality factor of any coil can be decided based upon how much of resistance present inside that coil. Okay, so you have seen in resonance concept that the quality of a coil, quality factor Q is nothing but here quality factor of an inductive coil can be found using the expression omega L by R. Okay, so as there is no capacitance which is available in this bridge, there is no chance to get resonance. Okay, as there is no chance to get resonance, we cannot evaluate the quality factor in case of this basic bridge. Okay, now how to draw the phasor diagram for this bridge? Okay, um, for this I want to copy this diagram. Let me copy it. Now if you observe, we'll just draw the phasor diagram under balanced condition. Under balanced condition, the current through this detector is 0. So the current through the detector is 0 under balanced condition. Now you have the same current which is flowing through this uh, arm as well as this arm. First arm and second arm, you will have same current. So I am assuming this current as a total current coming from here to here as I1. and I am assuming this current because there is no current here also. So you will have only one current which is flowing through the second and the third arms. So I am considering this as I2. Okay, so let me give a separate color for that so that you can understand it easily. So this is I1, this current is I1, and I am assuming this current as I2. I2. So for simplicity, for understanding the phasor diagram in a simple way, what I am trying to do is I am considering the currents as the reference, and both the currents are on the same line. Okay, I am assuming this as I1 and this as I2, both the currents like this, in order to draw the phasor diagram in a simple way, in order to understand it, right? Now, so my suggestion is start from the voltage drop, which is very simple to obtain. Okay, so here if you observe, this is R3 and this is R4. So I made a mistake here. This is E4. This is E4. Okay, now if you observe, the current I1 is flowing through the first arm and third arm. Now what is this drop? I1 is the current, R3 is the resistance. So E3 can be written as I1 into R3. Is it right or not? So now this is the reference. Now I am assuming this drop as I1 into R3. Now what is this I1 into R3 equal to? I1 into R3 is same as I2 into R4. Why? Because as the current through the detector is 0, these two ends are at the same voltage, and this end is common, this for these third and fourth arms, this end is common, and these two ends are at the same voltage if the detector current is 0. So the voltage E3 is same as E4. Okay, let me write here for your better understanding. Under balanced condition, under balanced condition, the current through the detector is equal to 0. It indicates that E3 is equal to E4, and also what about E1 and E2? E1 and E2 must also be equal because the current through detector is 0. These two ends will be in the same potential, and this end is common for both the arms. Hence, E3 is equal to E4 and E1 is equal to E2. You must also understand one more fact, that the total voltage E is the phasor sum of these two voltages or the phasor sum of these two voltages. Okay, let me write that fact also. So E is the summation of E1 and E3, or it is also equal to the summation of E2 and E4. Okay. Now what is I1 into R3? I1 into R3 is equal to E3, and it is also equal to E4. And what is this E4 equal to? The voltage across these two terminals is the product of current I2, because it is the same current flowing through second and fourth arms, and I2 into R4. So E4 is equal to I2 into R4. In addition to that, I am assuming that the uh, let me write like this. So this I2, I1 now we got here. In addition to that, I am assuming that I1 into omega L1, or let me write here. I am considering another drop. Why? Because how can I get even? How can I get even? Even is the summation of two voltages. What are the two voltages? I1 into R1 is 1 voltage, and J omega J I1 into omega L1, or I1 into J omega L1 is another voltage. Okay, so this I1 R1 is the voltage in between these two terminals, and I1 omega L1 is the voltage across the inductance. voltage across the resistance and voltage across the inductance. When you add these two voltages, you will get this voltage, but the summation is the phasor sum, right? Now I am considering this drop up from this point to this point as I1 into R1. For simplicity, I am also considering this drop is same as this drop. So I1 into R1 I am considering as equal to I2 into R2. When I1 R1 is equal to I2 R2, now I1 omega L1 must also be equal to I2 omega L2. Okay, so how it looks like? It looks like this, because this is the resistive drop for this coil. Now how will be the inductive drop? Inductive drop must make an angle of 90 degrees with the resistive drop. So I am considering this as I1 omega L1, and it is also equal to I2 omega L2. Okay, for simplicity I am assuming that the voltage drop across this resistance is same as the voltage drop across this resistance, and the voltage drop across this inductance is same as the voltage drop across this inductance, for easy understanding, for simplicity. So that from this point to this point it is a resistive drop I1 R1 from this point to this point, and from this point to this point it is inductive drop. The resultant of these two, is it right? The resultant of these two is E1. So this is E1. Why it is E1? Because the resultant of the resistive drop, if you observe here, you can understand this. The resultant of the resistive drop, and what is this drop? This is inductive drop. Both have 90 degrees because you have J. The resultant of the resistive drop and the inductive drop is E1. And what is it? It is also equal to E2, because the detector current is 0. When the current through detector is 0, both are at the same potential. So E1 is equal to E2. Hence, I can write here itself E1 is equal to E2. Now you got E3, E4 at this point, which is I1 into R3 or I2 into R4, and E1 is equal to E2 at this point. Now you need to consider this one. What is this? The source voltage is the summation of, let me show here. The source voltage is the summation of either E1, E3, E1 here, E3 here, or E2 and E4. So E2 here, E4 here, right? Now the resultant of these two phasors. Okay, so this is phasor 1 and this is phasor 2. The resultant of these two phasors, how can you find? Just draw a parallel line to the phasor 1. Similarly, draw a parallel line to the phasor 2 like this. This is the point. Join the origin and this phasor. Now what is this? This is E. E is the resultant of E1, E3 or E2, E4. Finally, we got this E. Okay. In this way, you can draw the phasor diagram by just considering some simplifications, means some assumptions. That here the basic assumption for drawing this phasor diagram in a simple way, the assumption which I considered is the voltage across this resistance is same as the voltage across this resistance, and the voltage across this inductance is same as the voltage across this inductance. This is the small assumption which I have taken in order to draw the phasor diagram in a simple way, and the remaining all things obtained from the balanced condition. Under balanced condition, you will have the detector current is 0, so E3 will be equal to E4, E1 will be equal to E2, and E is the summation of this.